All right. So it is important for us to know what these degrees of freedom are. And these degrees of freedom are simply the unknown displacement that a node will undergo. All right. So if you have an unrestrained node, like for example, the node here, the node on at this very point, let me just highlight that one. So the node over here is unrestrained. It means that there's no support, there's no joints. It's allowed to move anyhow it wants if you apply some load to it. So the number of movement, direction-wise, and all that is what will determine the degree of freedom. All right. So for each node, we need to know what each degree of freedom is. All right. Then once we know the degree of freedom of each node, so we should be able to determine. So the degree of freedom is written as DOF. Determine the degree of freedom of each node on a structure. Okay. Then also, once you know each node, and then if you're able to determine the degree of freedom of each node, then we can sum up the degree of freedom of all the nodes on a structure. Okay, so once we do that, these then become the unknowns, all right? So this becomes then the total degree of freedom become the unknowns. Okay. And that these unknowns are what you refer as or the number of unknowns, the number of unknowns, but these unknowns have to do with the degree of freedoms. Okay. So these are referred to as the degree in which the structure is kinematically indeterminate. Let me just scroll down a little bit. Kinematically indeterminate. Okay. So we've looked at indeterminacy already when we're looking at the basic structures, where we're focusing on the statistical classification of structures, right? The difference between these two has to do with the fact that with the statistical classification, where we're looking at we were focusing more on the external behavior. Okay, so we're comparing what supports reactions with equilibrium equations. Support reactions. So we're comparing support reactions with equilibrium equations. So this was more of external response. whilst with the principle of kinematics, we are looking at motion, the movement of joints, all right? So this movement of joint has to do more with an internal behavior, all right? So the extent with which each joint would move in whichever direction when the loads are applied is what we call the kinematic indeterminacy, all right? So let's look at what they are, what this kinematic indeterminacy is. Now, if you have a structure in, okay, so this is, if you have a structure in a 3D space, so for a structure in a 3D space or a three-dimensional space, so let's say a typical example is something like this. Okay, and we have these joints or these nodes. There's one also hidden at the back somewhere. Okay. So let me just, we'll see this portion. So we have these nodes right here on this structure. Take this node, for example, okay. This particular node can move upwards or downwards. So it can move vertically. So assuming I have this to be, let's say, oops, if this is Y, this is X, then this is Z. Okay, let's make it that way. So three-dimensional space, so it can move up and down in the Y direction. It can also move along this line. So it can move along this line, right? So that it can move in the Z direction, it can go this way along the line I'm trying to show right here. So it means that it can also move in this direction, go and come for that particular node. In the same way, it can also move in this direction as well. So it can also move in the X direction, while this is the Z direction. So it means that a node can move in three linear displacement or linear or translationally, it can move in three directions. All right, so this is for three linear displacement. Okay, and then for any node, it would not, or for an unrestrained node, it will not only undergo linear displacement, but it can also undergo rotations. All right, so it can rotate about the x-axis. It can also rotate about the y-axis. It can also rotate about the z-axis. So whilst it's having three linear displacement, it also have three rotational displacement. So that if you have something like this, then you have rotation about this, rotation about that, and rotation about that. So our nodes can have rotations about what's the name? Both the X, Y, and Z axis. All right. So in a way, I can say that we can have, let's say, delta X, delta Y, and delta Z. Okay, so these are the linear displacements. And then we can also have theta X, theta Y, and theta Z. So these are the rotational displacements. Okay. So for any three-dimensional structure, okay, the maximum the maximum displacement it can undergo is 6, which means that the maximum number of degree of freedom for a node in 3D is 6. All right. 3 for translational and 3 for rotational. All right. So this is the maximum. So it's not always the case that you find all your nodes undergoing all 6 displacements or all 6 degree of freedoms, right? Sometimes you might have some restraints which will prevent them from experiencing all 6. In some cases, they might not even experience any of these degree of freedoms. Okay. So this is for a 3D space. Now, what if we have a 2-dimensional structure, which is mostly how we analyze structures? So for a 2-dimensional structure, someone's mic is on. So for a 2-dimensional structure, for example, if I look at let's say a cantilever, for example, the most basic of them. We have these nodes at these ends. All right. So with this being, the node can deflect upwards. This node can deflect horizontally. It can also rotate. About this point. So for any 2-dimensional objects, our nodes would experience a displacement with respect to the y, respect to the x, and also a rotational displacement, a rotational about the z. So we have let's say in fact we have theta delta x, delta y, and then theta z. Okay. So for any node in a 2-dimensional space, the maximum number of degree of freedoms we can have is 3. So for any node in a 2D structure, the maximum number of degree of freedoms or unknowns is 3. 2 translational, so these ones are translational, and then 1 rotational. So that's something for us to know, all right, which means that for this particular course, we'll be focusing more on 2-dimensional structures. So it means that we are assuming that every node on our structure would have at most 3 degrees of freedom, all right. Oh, degrees of freedom again is just simply means for an unrestrained node, which directions can they move? All right, like freely, right? Freedom. Okay. So let's look at some examples of how this whole thing works out. Okay. Let's say I have let's start with a cantilever again. I have two nodes at these ends. Let's say I apply some point load P to it. Okay. It means that my beam is going to deflect, right? It's going to deflect in this way. Okay. So this is the deflected shape of my beam. Okay. What it means is that this node, which used to be here, has now moved down here. So the node has undergone some vertical displacement. So let's call it delta y. At the same time, there's been some rotation, some horizontal, so I can draw. So there's been some angle here. So let's call that angle theta z. Okay. So this particular node, node 2, has undergone two displacements, one translational and then one rotational. So the number of unknowns for node 2, the number of unknowns for node 2 is equal to 2. Now let's come to node 1. Okay. Now if you look at node 1, because of the fact that there's a fixed support over there, that fixed support will not allow any form of movement of that node. All right, which means that the delta y at that point should be 0, then the sigma z is also going to be 0. Okay. Which means that for node 1, the number of unknowns for node 1 is equal to 0. Are we here? So that if you sum them up, you get 2. So 2 degrees of freedom. All right. So then we can say that this structure is kinematically indeterminate to the second degree, because we only have 1 degree of freedom, 2 degrees of freedom, sorry. So it is kinematically indeterminate to the second degree. Simply means that we have 2 unknown displacement we need to find before we can find our reactions. Any questions?
Yes, please. The node 1.
Yeah.
Please, you said the number of unknowns for node 1 is equal to 0.
Yeah. Mm-hmm.
Isn't it 1?
Explain why you think it's 1.
Because there's one node there.
Yeah, there's a node over there. The number of the unknowns has to do with the degree of freedom. Okay.
Yes.
The degree of freedom. So if you take the node, okay, and then the degree of freedom has to do with the displacement of the node. So now
Okay.
a node.
Okay. Please, I've gotten it.
Sure. So the degree of freedom has to do with the displacement of the node. So can the node displace? If the answer is yes, in which directions can it displace? Then you can know how many ways it can displace. But if it can't, then it means that it has no degree of freedom. All right. Okay. And these ones, we looked at them when we were looking at the conjugate beam method, right? Where we could tell whether a support would have some displacement or not, depending on what support we had. Okay. So it's the same idea being transferred over here.
Okay.
So there are some more examples. So let's look at some one or two examples. So we can see here that nodal displacement, or the displacement of the nodes, can be restricted by the supports. Okay, so considered by the supports. So that is one, as we just seen. By the, what's wrong with my handwriting today? So by the supports, and then also due to assumptions based on the behavior of the structure. Okay. At least we've seen how the support can restrict or constrain the nodal displacements. And in the case of assumptions based on the behavior of the structure, for example, for beams, when I was discussing this particular, this one right here, when I was looking at it, I did not mention anything as to sigma x, right? I didn't talk about the horizontal deflections, right? Because we are assuming that if you have a configuration, if you have okay, this is quite strange. So if you have a beam whereby the load is vertical, which means that there will not be any horizontal motion of the load. So we can assume that for most beams, we are only looking at what only bending behavior. All right. So with only bending behavior, there will be no axial motion. So no axial which means that technically we're not concerned about our sigma x. We are not concerned about it. Okay. So in that case, we are only focusing on total sigma delta x. So we are focusing on delta y, which then we can call it delta, and then theta x, which we can simply call it theta. All right. So we are focusing on only these two. Okay. So which means that we can actually reduce the kinematic indeterminacy to just the two terms, either delta or theta. Okay. So in the case where we have, let's say, an overhanging beam, okay. So this is joint A, joint B, and joint C. All right. So that this is node 1, node 2, node 3. We prefer to name the nodes with numbers instead of with alphabets or with letters. All right. So this, if I apply a point load at C, all right, it means that our beam will undergo a deflection like that. Okay. So once that happens, it means that we can determine this angle here will be theta, let's say theta A. We also determine an angle here this will be the same. So there would be theta b. Then we can also have our other angle over here. This doesn't look. So let's say we can have maybe a tangent here. We have this angle. So this becomes theta c, and also have this deflection here, delta. Okay. So for this particular structure, we have 1, 2, 3, 4. So we have theta A, theta B, theta C, and maybe delta C. Okay. So in all, we have 4 unknowns. Okay. So basically, this is what kinematically indeterminate to the 4th degree. If you have to look at this in terms of the statistical classification, then this beam is what statically determinate. Yeah. But then in terms of the displacement, it is kinematically indeterminate to the 4th degree, which means that if you apply a load to this beam, the beam is going to deflect at point C and downward deflection. Then also at the various support conditions, there's going to be rotations occurring. All right. Now let's look at another example, and then let's say we have a frame. Let's say we have a frame, then we apply a load P to this frame. It means that the frame will undergo, so if this is, let's say, let me just label this point A, B, C, and D. I'll make it smaller. Okay. So C and D. Once apply this load P, then our beam is going to undergo some it will undergo some deflection like that. Okay. So this is how the beam is going to perform. It's a good way of drawing it, but at least this is just for us to get an idea of what goes on. This one looks a bit funny. Okay. So something like that, yeah. So we can see that our B has now moved to a point called B prime. This is our C prime, okay. So there is some deflection here and some deflection here. So let's call it going to be delta B, I call this delta C, okay. And at the same time, we'll have some rotation also theta B, and also have some rotation here, theta C. All right. So in a case whereby theta B is equal to theta C, then we have, sorry, delta B is equal to delta C. Then we have only one delta because of the way the configuration is. In some cases, it might not be the same, but here, because they all have the same length, the same column heights, the same, with only one load applying at point B, it means that delta B is equal to delta C. So here we have one delta, and also we also have theta B, also have theta C. Here, there won't be any theta A or theta D because this pointer was fixed. All right. So point A and D are fixed, which means that they are restricting the nodes, these nodes at these ends from moving. So at point A and D, the nodes at those points will not undergo any displacement. So it means that this our system has three unknowns or 3 degrees of freedom. So it is kinematically indeterminate to the 3rd degree. So it's based on these unknowns that will formulate an equation, these unknowns. So the slope deflection equation will be based on these unknowns. All right. And that's one thing to take note of. Okay. So being able to specify the kinematic indeterminacy of this of the or the number of unconstrained degrees of freedom for the structure it's a very important step or first step when we are trying to apply the slope deflection method. All right, so in any cases or in any case, before you can even solve any problem, you need to identify what the degrees of freedom are, period. Otherwise, you can still formulate an equation, but the equation might not be correct because you have not identified what the degrees of freedom are. All right. Okay, so it's 7:22. No, sorry, I'm using my time. What will be the time in Ghana? 11:22, I think. Yeah. So let's take some 10 minutes break so that we, because I've started something entirely new. So let me just let's take the break and then we can continue at 11:32. All right.
Okay, sir.
Okay.
All right.
All right, so before the break, we were looking at the degrees of freedom. All right, and I have mentioned that it is important that as our very first step, we determine the degrees of freedom of the structure. All right, so now let's see how to formulate the slope deflection equation. Okay. Hopefully we can get it done before our time is up. Or wherever we get to continue next week. Okay. So formulation. Of the okay. So now let's look at a beam. A typical beam. So let's put a roller support here and then a pin support at one end. Let's say it has some arbitrarily loading on top of it, a UDL, and then maybe some point load P also acting. So this is W, X, this is P. Okay. Let's also say that there are some bending moments acting on this end. Let's call this one MAB. So this joint is joint A and then joint B. Okay. Then when we apply this load, the beam undergoes some deflection, okay, or some deformations, okay. So let's also assume that the joint or the supported B also deflects downwards, so that now this becomes a new position of your the new position of your. Let me just do this again. Okay. So this becomes, so this point is let's say B prime, okay, so that it undergoes some deflection delta. Okay. Then at the same point, you also have another moment MBA. Okay, so we are looking at a general situation, a beam experiencing all these at a go. Okay, you don't find that happening all the time where a beam would experience rotations and deflections and have moments at the ends and all that. We are trying to look at a more general approach in solving these types of problems. All right. So in this case, if I draw a tangent to joint A, I have theta A. If I draw a tangent here, I have theta B. All right. And then assuming I join A and B with a straight line. Hopefully I can draw a straight line. I used to have a ruler somewhere. I can't find it. Okay. Hopefully I can draw a straight line without making it really weird. Oops. We didn't end up becoming a straight line. Nowadays, deleting this thing so we can be funny. Okay. I have no other option. So let me just assume that this is a straight line. Okay, please. Let's assume it's a straight line. Let's assume this also goes here. Okay. So if I go this way, so this is AB and this straight line, okay, B prime. So this straight line is called a chord. It's the same thing, I'm just redrawing. So this straight line is called a chord. Now the angle, let's mix with the chord, let's call it psi. Okay, so this is psi, PSI, psi. Okay, so this angle here is psi. Okay, then this curve here is supposed to be the deflected shape or the deflected curve. Okay, then this is the chord. Here is the chord. Great. Okay, so in general, this is what we would experience when we have a beam that is our length L. Okay, so now let's assume that our EI is constant. Okay. EI is constant, so the flexural rigidity of the structure is constant throughout. So now let's look at a few terms. We have the MAB and then MBA. So the MAB and the MBA are what we call the internal end moment. Okay. So basically what we're trying to do is that we want to formulate equations of the various displacements in terms of the loads, where these loads are now the moments. Okay, so that if we can rewrite the equation in terms of the moments, then we can easily solve our displacements. Okay, then we have theta A, we have theta B, and also delta. So these are the three DOFs, okay? Then here is in delta. This information will be very useful to us as we go along. Okay, we have done something similar using the moment area method. All right, something very similar to this. Okay. So let's see. So theta A, theta B, and delta are the three DOFs. And also we, oops. So the delta here is supposed to be the relative displacement, or in some cases we can call it settlements when the okay. So relative settlement between the supports. And then the IV, which is the psi, so rotation of the member core. I think I've defined what everything is. And then Z and WX, and then P are the external loads. I think I've covered everything I need to from here. So these are the key things we need to take note of. One is the internal end moments, MAB and MBA. If you take, for example, this one right here, all right, MAB is the moment acting at A with respect to member AB. Now, if you look at MBA, is the moment acting at joint B with respect to the member AB. All right, so that's something that we just need to have at the back of our mind. Okay, why we have MAB and MBA. Now, let's look at something before. Let me just show you. All right, so let's look at so if you look at this very equation over here, this very diagram over here, if this length here is L, then it simply means that I can rewrite another equation in terms of that. Let me just put that into this bracket here. Right. If I'm to use tan, and then so means that what tan psi is equal to delta over L. So for very small angles of psi, we can assume that tan psi is approximately the same as psi. All right, which means that looks like my bubble is too small. which means that you can say that, okay, then psi is equal to delta over L. Okay. This equation will be useful to us very soon. Okay. So psi is equal to delta over L. And in most cases, the amount of deflection that a beam or a structure would experience, or the settlement that a structure is going to experience, is very small. So small that the angle is also so small, to the extent whereby we can assume that the tan of that angle is the same as the angle. All right. So once we have that, we can then look at the sign conventions. Sign conventions are very important in these analysis. Before we try to even solve this problem, let's look at the sign conventions. Okay. So one moment, okay, and then angular or rotational displacements are positive if the act clockwise, in this clockwise, if the act clockwise. Right. So if your if your moment and your rotations are clockwise, then they are positive. So for example, if I take a beam, or let's say a frame, okay, and I'm focusing on this joint here, and I say that, okay, this is A, B, C, and D. So I have a moment here. Oops, this is too big. I have moments here. Let's see. Let me call this one NBA. And let me call the green one here MBC. And this sign convention, it means that, and it means that our MBA will be negative. Sorry, positive because it is clockwise. So MBA is clockwise. Let me just use the red too, so that MBA is clockwise. All right, so that makes MBA positive. So assuming that it is, let's say, 20 kilonewton meter, then this is equal to 20 kilonewton meter. Okay. Then MBC is counterclockwise or anti-clockwise. Okay, so this will be negative, which means that we get what, negative 20 kilonewton meter. All right. So it is important to understand that sign conventions are critical, because otherwise you might end up with the wrong information. Okay. Now let's look at another example of how sign conventions are important to us. Now let's look at a beam that is undergoing some deflection. Let's look at a deflection like this. All right. So here, this is theta A. So here is theta B. The same here as theta B. Then on this end, we have theta C. All right. So which of these ones are positive and which of these ones are negative? All right. So theta, so we have theta A, theta B, and theta C. Okay. Now, if we look at theta A, this is the direction it goes, right? It starts from there. It rotates with respect to the with the beam. It rotates towards the clockwise direction. So that will make this the theta A positive. Now, if you look at theta B, it rotates this way towards, so it rotates against the clock. In both cases, it's rotating against the clock. So that will make theta B negative. Now, if you look at theta C rotates the same direction as the clock. So that will make theta C positive. Okay. So these are sign conventions for us to take note of. And the next sign convention to look at is the displacements or the settlements. Okay. So the settlement delta is positive if the right side supports the right side supports is below the left. Okay. And then delta is negative if the left side support is below the, okay, so let me just add this one, left side support, so that it becomes one complete statement. The right side support. Okay, so I'm going to explain how this works, and all of this information is critical. All right, so I can rewrite this information all into one that says that delta is positive if the chord of the span and the angle psi rotates in the clockwise direction. So let's say rotates clockwise. All right. So it's either this or that. So individually, it's, if you take if we take, for example, let's say I have a beam. So beam, say A, B, and C. Okay. So let's assume that the B would undergo some settlement. So now B is now at this point. Okay, which means that our structure has the shape now. So now this is the shape of our structure. This distance here, oops, this distance here is now our delta, which means that I can find my, if I draw a straight line between A and D, this is my first chord with an angle psi. And if I also draw another one between C and B, this becomes my chord psi 2, sorry. Okay. Now, if I'm looking at span AB, all right. So if I'm looking at span AB, my delta is positive. Okay, because per my definition of the sign convention, delta is positive if the right side support is below the left side. So if I'm looking at only span AB, then it means that with respect to AB, my right side support is B, and B has dropped lower than A. So that makes the delta positive. Again, if you look at the second definition, it says that delta is positive if the chord of the span and psi rotates clockwise. Okay. Now, if we take span AB, this is what we have. This is what we have. So this psi is rotating in a clockwise direction. So it makes our delta positive. Okay. So in that case, psi would also be what? Would also be positive. Okay. Now, if you look at span, BC, okay. So with span BC in mind, our delta is negative, okay. And it's because if I look at span BC, B is on the left and C is on the right. And per our sign convention definition, delta is negative if the left side support is below the right side. Okay, and B will be below C. So in this case, this is what we have. So this is B prime. So that is below C. And once the left side is below, this point is below the right hand side, then our deflection is negative. All right. Or our rotation of the chord, the side 2 is anti-clockwise or counterclockwise. So because it is counterclockwise, our deflection is negative. Okay. So these are sign conventions which are very critical to us as we go along. And we need to understand how these sign conventions work. Okay. Now let's see how we can formulate the equation. So the slope deflection equations as it can be completed by using the principle of superpositions. By considering so we want to look at how to use the principle of superimposition. So here we're looking at the case whereby the slope deflection equations can be completed by using the principle of superimpositions by considering separately the moment at each support due to each of the displacements. Okay. So in this case, our displacements are theta A, theta B delta. Okay, so we'll look at the displacement and also the loads. Okay, so in that case, we'll try to have a case whereby we have our beam uh, broken into 4 different parts. That once we add all these 4 sections together, it will still give us the initial beam that we have. So we are looking at this very one over here. So our focus still remains on this guy right there. That's what we're trying to do. So let's look at formulating equations for only theta A. All right, so now let's look at the angular displacement. At A. So in that case, we're looking at theta A. So for us to have a case whereby we can only have theta A in our structure, and it means that if I have a beam looking like this, okay, and I apply moments at these ends, let me call this ones MAB and then MBA, then it means that my beam would experience this type of bending. All right, or the deflected shape will be this type of bending, which means that I have my angle here, theta A, and that will be about it. Because from this formulation, our theta B will be equal to 0. Our delta B will also be equal to 0. This is A and B. Okay. And also, there are no loads on the structure. So at least for now, we can only solve for theta A. Okay. Then once we're done with solving for theta A, we'll formulate another structure where we can solve for only theta B. The other structure solve for only theta delta. Then another one also solve for only the loads. Then once we are done, we sum everything up. Okay. Now we have a beam. Okay, a propped cantilever beam, and we need to solve for it. So we need to find our MAB and find our MBA. Okay. And also know what our angle theta is. Okay, so now we have a beam of length L. Okay. So what do we do? How do you go about solving this type of problem? Okay. The easiest approach is to use the conjugate beam method. Okay. All right. So I can just come here, have a beam with this load acting on it, and it's the same as I can break this into 2 plus so that if I sum beam 1 and beam 2 together, I should get the original beam here. So that if this is my MAB, here's my MBA, MAB, MBA. We have looked at the principle of superimposition, I think, last semester, and I even explained to us that, for example, if you have a beam, okay, let's say maybe a series of loads acting on the beam, we can break the beam into the sections whereby we have one case with only one of the loads, with another case with the other load on it. Okay. So that if you find, let's say RA1, you find RB1, here you find RA2, and then RB2. And if here is RA, and this is our RB. It simply means that your RA is equal to RA1 plus RA2, and then your RB is equal to RB1 plus RB2. All right, so that's the idea with which we are working with. Okay, we're just employing that principle in solving these types of questions. Okay, so this is just something on the side. Okay. Let's see if everything is okay. If that up to normal. All right. So that's just on the side for us to take note of. All right. So here I have two beams. I can solve them separately. So now let's look at beam one. Let's look at beam one. Okay. So with beam one, let me just redraw that over here, just for clarity. I have my AB. Now, we have VA or RA, VA, and this is what VB. Okay. So if we say, let's say summation of moment at B equals 0, then it means that VA times L plus MAB equals 0. Okay, which means that our VA will be equal to minus MAB over L. Okay. Then if you have our X moving from here towards that, we want to draw the Venn moment diagram, okay? So it means that our moment at any point X will be equal to MAB plus VA times X. Okay. So that we have MAB minus MAB over LX. Okay, where I'm just replacing the VA with whatever we had previously. All right. So if X is equal to 0, then our MX is equal to MAB. And then if X is equal to L, our MX is equal to 0. So there our definition. This is our Venn moment diagram. Okay, where this point, so it's positive, so here is MAB. Okay, so that's for beam A. Now I can do something similar for beam B. So for beam B, I come again, draw the entire thing, but this time around I'm using the second beam, so this is my MBA. I want to find the VA here and then the VB also. This is simple basic structures that we are trying to use over here. You have a simply supported beam with a point load at a point moment at the end. So you find your reactions VA and VB. All right, in this case, I only solve for VA because I only needed to find only one of the reactions. All right, so for B1, I said let's do summation of moment about point B to be equal to 0. Then I wrote an equation in terms of that okay, if B is our point of interest, then the summation of moment at B will simply be VA times L plus the point moment, okay? And because it's a point moment, it doesn't need you to multiply it by any length because it's already a point moment. Then based on that, we're able to find our VA. So VA is equal to minus MAB over L. Then I also want to draw the bending moment diagram. Okay, so I write an equation to draw the bending moment diagram, and based on that equation, this is my bending moment diagram. Okay. So we apply the same idea to beam B. So for beam B, let's also say summation of moments about B equals 0. So our bending moments, our equation will be VA times L plus MBA equals 0. Okay, they both will go in the clockwise direction. So that's how come the equation has a plus in there. Then if you make VA the subject, you get minus MBA over L. So now we know what VA is. Now, if you have our X starting from A towards B, then again, our moments X along the span AB will be equal to VA times X, which is the same as minus MBA over L times X. Okay. That's where X is equal to 0, our moment at that particular point will also be 0. And then where X is equal to L, our moment at that point will be equal to minus MBA, which means that our bending moment diagram for the second beam would be a negative diagram. So this is negative, and the value here would be MBA. Okay. So based on that, my bending moment for so what I'm trying to do is just to draw the bending moment diagram for this particular beam right here. Okay, which is the same as the one that we are trying to solve for. Okay. So once I do that, it means that my bending moment diagram for the entire beam, if I'm using principal superposition, then I end up with bending moment diagram looking like this. So this one is negative, this one is positive. So this is your MAB, and this is your MB. All right. So now I have my bending moment diagram drawn. The next thing, because I still want to find theta A. All right. And we want to use the conjugate beam approach to find theta A. We know that in the conjugate beam approach, shear force in a conjugate beam is the same as what the rotation or the slope theta in the real beam. Okay. And then we know that the bending moment or the moment in the conjugate beam is the same as what the deflection in the real beam. We've done these ones already. So we are only applying that information from last semester here. Okay. So now let's look at the conjugate beam. Okay. The real beam, this is how the real beam looked like. It had a pin support at A and then a fixed support at B. Okay. So that if your real beam looked like this, so this is our real beam, then it means that our conjugate beam will look this way. Okay. If it's fixed, if the end is a fixed support at the in the real beam, it becomes a free end in the conjugate beam. All right. So the next thing is to load the conjugate beam with the M over EI diagram. So I have my conjugate beam, then I load it with my bending moments. So here is MAB over EI, and this is MBA over EI. Okay. The directions, we assume that positive will move away, or they all move away, respective of whether they are positive or negative. All right, so this is my A prime and my B prime. Okay. What I want to do is to find the rotation at A, right? I want to find theta A. So theta A in the real beam, RB, is the same as VA in the conjugate beam, or VA prime. So once I find VA prime, I've found my rotation. All right, theta A. Okay, and theta A is clockwise. Okay, theta A is clockwise, which we have established over here already. Theta A is clockwise. Okay, so because theta A is clockwise, it means that our VA will be downwards. Okay, VA or VA prime, sorry, will be downwards. Okay, these are things that we have already established. Okay, so VA will be downwards. So now let's see how we can find VA. So now we need to know what VA is, or VA prime will be. Okay. So let's write two equations. First one is summation of moment at A prime to be equal to 0. All right. So again, there's no reaction at B because B is now become a free end. So let's see. So let's start with the first triangle at the top. It becomes so we have MAB over EI, okay, times L over 2. So this will give me the area of the triangle, all right, times L over 3, which is the moment arm, because you find the moment about A, the moment arm of the top triangle will be somewhere here. That distance becomes 1/3 of L. Okay, and then now cause a clockwise rotation about A. The second triangle below will cause an anti-clockwise rotation about A. So that becomes negative. So you get negative MBA over EI times L over 2, which is going to give you, so this whole thing is the area here. This is also the area times the moment from the centroid of this triangle to A becomes 2/3 of L. So it becomes 2L over 3. And all of this is equal to 0. Okay. So if you simplify these equations, you will end up with MAB L squared over 6EI minus MBA over 3EI L squared equals 0. So let's see. If we have to make MAB the subject over here, that means that our MAB will then be equal to MBA over 3EI L squared times 6EI over L squared. So that will give us 2 MBA. So simply put, our MAB is equal to 2 MB, oops, 2 MBA. We'll come back to this equation sometime later. Now let's also some moment about B. The summation of moments about B prime equals 0. So again, we go through the same process. Here our MBA over EI. If at some point you don't understand anything, please let me know. L over 2, which is the so this will give us the area times L over 3 minus MAB over EI times again L over 2 times 2/3 of L plus this case VA prime times L equals 0. Okay. We're taking moment about B, all right. So with the moment about B, it's about this very point. So the top triangle load and then the bottom triangle load. So we first start with the bottom triangle load, MB over EI, L over 2, L over 3. Then we do also for the top triangle load, which is the MAB, EI, L over 2 times 2, L over 3. Then we also add the shear force or the reaction at A, which is VA prime times L, all right, equals 0. All right. So from here, we can continue with our computations. So here the MBA L squared over 6EI minus MAB L squared over 3EI plus VA prime L equals 0. We know that our VA, the VA is the same as what theta A, all right? VA is the same as, or VA prime is the same as theta A. So I can just replace that by theta A. So I can just replace this one here by theta A, so that then I have, so I have, let's say MB, so now I have MBA L squared over 6EI minus MAB L squared over 3EI plus theta A times L equals 0. So now I have this equation to also have this equation right here. And also have these two equations, these ones, and then that one. So let's say equation 1, equation 2, and then equation 3. All right, so you can solve, I mean, we need equation 1, equation 3 anyways, only equation 1 and 3. So we can use equation 1 and 3 and then solve for the MBA. All right, but then we already have equation 2, so it makes things easier for us. So wherever we see, for example, wherever we see MAB, we can put 2 MB over there. So substituting equation 2 into equation 3. Okay. So once we do that, we'll end up with, let's say, so we have MBA L squared over 6EI minus 2 MBA L squared over 3EI plus theta A times L equals 0. All right. So once we compute this right here, if we add these two terms together, we'll end up with negative MBA times L squared over 2EI plus theta AL equals 0. So if you are to make MBA the subject, then it means that our MBA will then be equal to this. You go to the opposite of the equal to sign. It becomes theta A. Let me just do the steps for us. Okay, so MBA L squared over 2EI will be equal to theta A times L. All right. Okay. So it means that our MBA will be equal to 2EI over L squared times theta L. Okay. Which then is the same as 2EI over L times theta. Okay, so you've been able to write one of the moments in terms of the rotations, which means that once we're able to determine what the rotation is, then we can determine what the moment will be. And then once we know what the internal end moment are, that information will guide us as to what the reactions will be on the structure. So if MBA is equal to 2EI theta, then it means that we can also find our MAB. All right, so we can put this, I can put our answer back into equation 2 and find MAB. So our MAB will be equal to 2 times 2EI over L theta. And that will give us 4EI over L theta. So let's take a moment to go through all that we've done. It seems a lot, but then the, the idea or the fundamentals are pretty much the same in a way. Nothing really has changed. Okay, so I'm just going to run us through it for us to have a good understanding of what has happened so far. Okay.
So please, so do you use formulas like this in your work when you are actually working?
Do I use formulas like this?
Yes.
I don't know how. I don't know how your questions are done. But, do use formulas like this? We are trying to derive the formula, right?
Yeah, 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 but like when you are trying to like,
When we are trying to, sorry, I didn't hear that part. Hello.
yes sir, yes sir. Like when you are given a work and you're supposed to find like indeterminacy of like a structure or something, do you actually like use formula work to find it on the site?
On the site.
Yes, please.
So let me
Or before the site, or before like the creation of everything.
let me try to explain it to you in a more holistic manner. I think Wednesday when we met, we talked about the fact that in engineering we need to do analysis of a structure, right? And that lately there are computer programs that do the analysis for us, so we don't really do much of it. But then again, the computer might not be right because maybe the information that was input into the computer is not the right information. So these topics or these methods, like the slope deflection method, the conjugate beam method, and all other methods, are different ways by which we can do hand calculations to check if the information output by the computer program is correct. So we are learning these methods so that we can also be able to do or we learn these methods to have a fundamental understanding of what structural analysis is so that we can be able to tell whether when a computer program is right or wrong, or two, as engineers, we can be able to analyze the structure by using these hand calculations. All right. So now what we are trying to do with all that I've done so far is to develop an equation or a series of equations which we will need to analyze the structure using the slope deflection method. All right. So I don't know if I've been able to answer your question correctly.
Okay, sir.
All right. Yeah. So for now, we are only trying to derive the equation. We've not gotten to the equation yet. All right. We're trying to derive the equations and the derivation or the approach for this derivation is using the principle of superimposition. All right. So we are assuming that if you go all the way up here to the general diagram, we are assuming that for a case whereby the structure would experience both rotations at the ends of its member and also experience deflection at least one of the ends of the member. Then when we have such a case, how then do we come or how then do we solve it? All right. So we are trying to understand the fact that, okay, for in this case, there are three unknowns or three degrees of freedom, right? Theta A, theta B, and then delta. Okay. So um, let's formulate equations for when we have only theta A, which is what we are trying to do. Okay. Then we get the moment in terms of theta A, which was the final answer we had here. These two, right? These two right here. And then this one. Okay. So we found theta A in terms of the moments. Then you also need to find theta B in terms of the moments, delta in terms of the moment, and then the external loads in terms of the moments. Then we sum everything up to give us the end moments. All right. So in case one, when we're trying to looking at only the angular displacement at A, that's the theta A, we had to construct or formulate a beam which would experience only theta A. And that was a prop cantilever that we used. Okay, with a fixed support at A. Second, I don't know what is wrong with second, let me see. Okay. Let me just continue. I'll figure that one out later. All right. So all right. So in that case, we have a prop cantilever with moments at the ends of the prop cantilever, and we need to find these moments. So we need to find MAB and find MBA. But we are finding MAB and MBA in terms of the rotation theta A. All right. So again, we employ the principle of superimposition. We break the structure into easy to solve components. So we have components. So this has been two. Sorry, we have component one right here, and then component two. So when we sum these two different beams together, we'll get the original beam. Okay. So for beam one, we have moments at, or a point moment at A called MAB. Then we find the reactions VA, and then we draw the bending moment diagram. Okay. Then we also come to the beam two, go by a similar approach, find our MBA, determine our moment MBA, and then draw the bending moment diagram. Okay. So once we draw these two bending moment diagram, this becomes the final bending moment diagram. Okay. For us. Then, because we still want to find theta A, we have to use the conjugate beam method approach, which we learned last semester. And with that approach, you have to convert your real beam into a conjugate beam. Okay. And we explained that if the real beam has a fixed support in the conjugate beam, it becomes a free end. All right, so that's where we move from the real beam to the conjugate beam. Okay. So so once we have the conjugate beam, we load the conjugate beam with our M over EI diagram. The M over EI diagram is simply the bending moment diagram divided by the flexural rigidity. Okay, that's the EI. The E is the Young's modulus. The I is the moment of inertia. All right, and from your strength of materials class, you learned that your moment of inertia is the ability of the material to resist what's the motion, mostly rotational motion. All right. So once we load the conjugate beam with our M over ER diagram, then we can solve for VA or VA prime. Okay. And then to do that, we formulate two equations. Summation of moment about A prime to be equal to 0, and then summation of moment about B prime to be equal to 0. So we have two equations that we solve for MA, or we solve for MAB, and then also solve for MBA. That we end up with these two equations, whereby MBA is equal to 2EI. So we end up with let's say MAB is equal to 4EI over L theta A. Then our MBA is equal to 2EI over L theta. Sorry, theta A. Okay. So these are the moments MBA and MAB based on the based on the case whereby we only have the angular displacement theta A. The next thing to look at will be the angular displacement. At B, which is theta B. Okay. So to have a beam experiencing only that, we also need to come up with a structure which would undergo only theta B, or only rotation at point B. So this is A and this is B. Okay. So we still have a moment MAB and then MBA. Okay. So in effect, this is how the beam is going to bend due to the moment acting on it. So we have a clockwise rotation, theta. If this is a tangent, then this becomes theta B. Okay. Now, to find theta B, the approach is very similar to how we found theta A, right? So again, I'll run through this one quickly because of the fact that we've already done the one for theta A. So for theta B, we have again the actual structure, this one, with the moment, and we break it into two. So we have one case here with the moments, the other case again with this moments right here. So we have our MAB here, and we have MBA. So this are beam one, and this are beam two. Okay, and then if you go by that approach, you end up with the same Benjamin diagram as it was in the previous case for the theta A. All right, so our Benjamin diagram would again look, so the Benjamin diagram will again take this shape. We have our MBA, here becomes MAB. Okay. Then we find a conjugate beam. Okay. And in this case, our conjugate beam, since it was fixed at A, it becomes a free end at A, but then the pin support still remains. So we load the conjugate beam with the M over EI diagram. So this becomes MBA over EI, and it becomes MAB over EI. Okay. So we need to find VB prime, and then VB prime the same as what? Theta B. All right, so the same idea with how we solve the first one is what we're trying to use to solve for the second method. Okay. So So if we do it that way, in this case, our our MAB will be equal to 2EI over L theta B. Then our MBA will be equal to 4EI over L theta B. If you want to solve them. I mean, we can go through the process and all that, but it's about the same. For example, if this is, you have A prime here, B prime here, I say summation of moment at, let's say, A prime equals 0, then we'll have what MAB over EI times what L over 2 times L over 3 minus MBA over EI times L over 2 times 2L over 3 and plus theta B times L. Theta B times L is the same as VB prime times L. All right. So we have this equation here. Sorry. Then the next equation will be theta MBA prime, or summation of moment about B prime to be equal to 0. So the same idea. We'll get MBA over EI times L over 2 times L over 3 minus MAB over EI times L over 2 times 2L over 3 equals 0, 2 here. And if you solve these two equations simultaneously, this will be your answer, and this will be your answer. All right. All right, so the next thing to look at, since we are almost running out of time, the next thing to look at will be the relative linear displacement. We'll look at that next week. Now you can read about them, okay, in the Hibla. So we are going to focus on delta and then the loads, and then also solve some examples from next week. All right. So this should bring us to the end of today's lecture. So just a quick recap. We've gone through a number of things today. We've gone through a recap of last week's topic. We've also looked at what the slope deflection method is, degree of freedom. We've also discussed what it means to have kinematic indeterminacy, and also formulate equations for the slope deflection method. All right, by looking at the angular displacement at A, and then the angular displacement at B. All right. Any questions?
No, please.
Relative linear displacements. Okay. So that's our delta. Okay. Now, before we start solving anything, let's understand the term relative. It's very important. Okay. So I'd explained earlier that if you have, let's say, the system, okay, typically the supports A and B do not displace because the support holds the structure in place. But then sometimes, depending on the soil conditions, your structure would undergo some minimal displacement. Or anytime you build a structure, some amount of displacement might be allowed, depending on the use of the structure and whether these displacements have been taken into consideration during the design process. All right. You know, anytime, let's say, for example, if you're walking and you step, and let's say, assuming, let's say it has rained, and then you walk in and you step into, let's say, a muddy place. All right. Sometimes when you step into this in the mud, you tend to like sink a little bit. You sink a little bit into the ground. All right, just a little bit. That's how buildings behave. All right. Usually, when the ground is not sufficient to hold them, they tend to settle. Okay. And in some cases, you can have a variety of cases. Maybe, let's say support A will settle, but B will not. Okay. Assuming we are looking at just settlement. Or some cases, support A will not settle, but B will settle. Or both A and B will settle, or will have the same settlement. Let me just use the word same settlement. Or in some cases, even though both A and B will settle, maybe B will settle more than A. Or where both A and B will settle, maybe A will settle more than B. So in all these cases, what is of interest to us is a relative set, is a relative term. So I'm going to go ahead and explain that shortly. So now we have case 1, case 2, case 3, case 4, and then case 5. Now let's look at the case 1. Or there's even a case 0 where none of them settles. Okay. So none of A and B settles. So that's the case 0. And with the case 0, it means that with or case O, it means that your delta is 0 because there's no settlement or displacement going on for any of them. Okay. But for case 2, or for case 1, if you have, so now your initial position is this. Okay, so this is A, and this is B, but then with time, this is how your beam now looks like. Okay, so that the support at A has now moved, and this support is moved, but this support remains the same. All right, so there will be some deflection delta. Let's call it delta A. Okay, so delta A here, oops, delta A here will be negative. Okay, we explained that already from last week. So delta A here will be negative. Okay. Now let's look at the second case, or case 2. With case 2, A doesn't settle, but B will. So something very similar to what you have over here. And then this comes down like that. Okay. So again, your support at B has moved, but the support at A has not moved. So this deflection right here, delta B. So delta B will be a positive displacement. So delta A is the same as delta. So this delta is actually the relative displacement. So this is also equal to delta. Okay. Now let's look at the case 3. So in case 3, they both displace or they both settle. All right. So we have the supports right here. Okay. And then they both undergo the same settlement. Okay. Oh, sorry. This is pin support and this is pin, and then the other one is roller. So this is a roller support, and this is a pin support. Okay, good. So here we have delta A, and also have delta B. Okay, but because they all underwent the same settlements, it means that delta A is equal to delta B. Okay, and if they both undergo the same displacement, then there's no relative difference between the two, which means that delta A minus delta B will give us 0. Okay, so let me put a delta here. So because the difference between them is 0, it means that this relative displacement that we are looking at, delta here, will also be 0. Because in terms of relativity, there's no difference between the two of them. All right, so if they both settle at the same, or they both undergo the same linear displacement, then the relative displacement of the entire system here will be 0. Okay, so let's take note of that. Okay, now let's look at case 4. So with case 4, again, they have their initial position. Okay, then with case 4, they both settle. All right, but then B settles more than A, so we end up with something like that. Okay, so again, this is your B, A, and A. Okay, here you have your theta and delta A, and here you have your delta B. Okay, so because delta B is greater than delta A, all right, and again, so it means that our delta here will be equal to delta B minus delta A. Okay, and then because B is on the right hand side and it's lower, it means that we'll end up with a positive value for delta. Then for the case 5, which is the last case, if you have again the same beam, but then this time around everything is reverse. So this oops. Sometimes drawing a simple line takes forever. Oops, I'm not getting the way I want it. Okay, let me just start this way. All right, we'll just go with that. Okay, so here we have the displacement. So this is pin here, and then so here we have delta A and delta B. Okay, so here delta A is more than delta B. I don't know why I wrote this. Delta B. Okay. So our delta here will be equal to delta, and because the effective delta will be leaning towards the A side, it means that based on our sign convention, this becomes negative. All right, so you find these scenarios with your when you're looking at slope deflection method. All right, okay. So now let's see how we can formulate an equation for the moment MAB, MBA for this particular structure. All right, so that whatever I wrote at the top are just to help us to understand what the relative displacement is. All right, so if I have a beam, okay, so both ends are fixed, okay, but then I can allow this end right here to undergo some some displacement. Okay, I'm using the B side because this is what will give me a positive delta. So here, delta is what? Positive. If I use the left-hand side, delta would have been negative. Okay, so now I need to find my MAB with respect to delta, and also find my MBA. Okay, so again, based on this, you formulate an equation for that. All right. The idea is the same as that of the ones we did last 2 weeks. So here, your theta A, your theta A will be 0. Delta, obviously, delta, this here is just relative delta, so let's just take it off. Your theta B will also be 0. Okay. And again, there are no loads. Okay, so this is 0. Right. So based on that, we can easily see how we can find MAB and MBA. All right. Okay. So the first point is to draw the bending moment diagram. So again, here you can use the principle of superimposition. You do for only MAB and you do for only MBA. All right. So if I were to use that principle, our bending moment diagram will look like that. Okay. So this is positive, and this is MAB. And then we have down here the negative, which is MBA. Okay. And this is based on what we've done already. So it's the same idea, same approach we used. Then once we get the bending moment, we can load the bending moment on the M over EI diagram. Okay. Or we load the conjugate beam with the M over EI diagram. So now if we take the real beam, right, the real beam has 2 fixed supports at the ends, right? So it means that if I'm to draw the conjugate beam, the conjugate beam here will just be a beam. So this is A and B. Okay. If it's fixed, or if it has a fixed support at A, then to be a free end at A in a conjugate beam. And then in the real beam, if the end is fixed at B, it becomes a free end in a conjugate beam. All right. So it means that A prime and B prime is how the entire conjugate beam will look like. So it becomes MAB over EI and then MBA over EI. All right. So this is how your conjugate beam is going to work. But then because we said that there was some deflection at B, we need to account for that in our conjugate beam. All right. So for that to happen, we place an end moment. We place an end moment here, which we call it MB or MB prime. Okay. So that this end moment at B, which is the MB prime, if we find this end moment, or we find this moment in the conjugate beam, then this particular moment will be the same as the deflection in the real beam. All right. So moment in conjugate beam is the same as deflection in the real beam. Okay. So these are things that we've looked at already in the what's the name? Theory of structures. All right. So based on this configuration right here, we can easily determine the moments MAB and MBA in terms of the deflection. All right. So let's say, let's start by looking at, let's say, summation of moment at A, or let's say A prime equals 0. So we're looking at the conjugate beam, all right? So typically these are the directions of our moment. Now the moments have become loads, so. Okay. So summation of moments at A prime equals 0. So now we'll have becomes MAB over EI So the area here becomes 1. So this whole thing is L. I forgot about the length L. So it becomes what the area of a triangle, which is what half base times height. So our height is MAB. It becomes L over 2. Then times the moment arm to A. And that'll give us what 1 over 3. All right. So 1 over 3L. So let's say L over 3. Okay. Then we'll have minus MBA over EI, again times L over 2, then minus MB prime equals 0. Okay. These are just directions of this. Minuses are how the moment works, all right, in terms of the rotations. Okay. About A, this will give us, MAB will give us anti-clockwise behavior. Then and then MB will be clockwise. It's also be clockwise. So it's just directions, all right. But we know that MAB or MB prime, sorry, is the same as what the delta we are looking at. So I can rewrite this entire equation and then have MAB 6 minus MBA over square root 0. All right. Then let's say summation of moment. So let me just do that one on this side. Hopefully it's able to fit. Oops. Okay. On these things, they always tend to freeze when they should not be freezing. So this is equal to delta. All right. So we can have another case. Oops. So summation of moments at B prime equals 0. And with that in mind, if you do the computation, you end up with MAB 2 times 2L over 3. If I can just put a negative there so that it doesn't change anything, plus MBA over EI 3 minus delta equals 0. So let's see if our angles make sense. So with respect to this, okay, so with respect to B, we will have so this will be anti-clockwise about B, and then this will be clockwise, and this will also be clockwise. So that if clockwise are negative, then fair, and then clockwise anti-clockwise are positive, that's also okay. You can just play with the directions. Just decide that all anti-clockwise are positive, or just make sure that one of them is positive and then the other set is also negative. Okay. So once we do this, we'll end up with MBA L squared over 6 MAB delta equals 0. So we have equation 1. Now we have equation 2. Equations 1. All right. So once we do that, if we solve equation 1 and 2 simultaneously, we would end up with our MAB being equal to negative 6EI over L squared. A will also be equal to negative 6EI, which means that when for this particular case, MAB, okay. So again, we'll come back to these guys later on. Come back to them later on. But for now, these are our moment. If you solve equation 1 and 2 simultaneously, this is what you end up getting. Okay. So now let's look at the final one. Okay, so let's take a 10 minutes break and then we'll come back. Oh wait, are we 6 to 7 is 1 hour? Okay, we have about 15 more minutes, so let's continue. We'll do the break later. Okay. So now the next thing to look at is the loads. All right, the loads on the structure. Okay, and these loads would help us to formulate what we call fixed end moment. So in previous cases so far, what we've been looking at is just considering the relationship between displacement and moments, right? So for this is just an aside. What we're looking at so far is in delta, right? And then MAB and then MBE. So that's what we've been doing for the past 2 weeks or so. All right. So we find MAB and then MBE are the nodes A and B. All right. But then typically these displacements that we are talking about are actually caused by the loads, right? So if there are no loads on the structure, these displacements will not otherwise occur, all right? So these displacements that we have been talking about, they are caused by, so the displacements are caused by load on the span. Okay, let's say the span of the member. So the displacement are caused by the loads acting on the span of the member or the members, and not the end moments. All right. So to develop the slope deflection equations, we need to transform. So we need the the span loadings. Okay. Equivalent moments acting. So the idea is that we take the loads acting on in the spans, and then see how we can convert these loads into what's the name? Into the end moments. All right. So that's the idea. So we need to find. So we find the reaction moments at the nodes. All right. Let's see. Oops. Okay. So this reaction moment at each node are what we call the fixed end moments. So let's say FEM. You find this term FEM being used a lot. It just means the fixed end moment. So let's look at a typical example. All right. So let's say we have, so in that scenario, we need to also come up with a loading system whereby we will not experience any of these. So whereby R equals 0. All right. So typically, and that's like how the name fixed end moment, because it's a beam whereby both ends are fixed or have fixed supports. All right. So we have something A and B. Okay. So once A and B do not undergo any displacement, it means that the deflections at that point will be 0, and then also the rotations at both A and B will be 0. All right. So let's say we have a point load P acting right in the. Okay. So in this case, what do we do? Because we need to find these moments. Oops. I need to find this moment. MAB. Hopefully, let me see if I got it right. The first one. Oops, I made a mistake here. Please, let's correct this. All the moments are clockwise. Let me just check to make sure that that's what I did for the others. A second. So let me check. Okay, so this one is clockwise. They all have to be in the same direction, clockwise. Let me check the other one too. Where are you? Okay, here you are. Okay, so they both, that's good. All right. So this misbehavior. Okay. So yeah. So in all cases, they're all clockwise. All right. So that if your MAB is negative, it simply means that it was anti-clockwise or counterclockwise. Okay. So let's look at the fixed support case. I don't know what's wrong with my screen today. Just give me a second. Okay, I think now let's finish should work. Okay, let me see. Okay, good. All right. So let's see. So in the case of the fixed supports or the fixed end moments, as we're looking at, with that one, we assume that these are the directions of our moment. We'll get to understand that soon. So here becomes our MA. Take note the directions of our moments. Okay. In all cases, they have always been clockwise, whether it's MAB or MBA. But in the case of the fixed end moments, now the left-hand side is anti-clockwise, and then the right-hand side is clockwise. So let's just take note of the change. We'll get to understand shortly. All right. So here, if we look at it, okay, we can use the principle of superimposition, whereby this entire beam can look this way. I can have one case plus another case whereby I have only MBA. Okay. So if I'm to use these three cases, so for case one, my binomial diagram will be a positive one, right? So this becomes what? It becomes so P L. This will have a positive moment. So this is how this one will look like with the negative. Sorry, here once I change the direction of the moment, this negative is also negative because here I'm using anti-clockwise. So sorry. Oops. Jesus, see. I think I need to. Okay. So let me redraw again. So this is MAB. Okay, great. This is going to be a negative. So we can sum their moments together and then use the conjugate beam approach and solve for the moment MAB and then MBA. All right. So they are combined M over AI diagram. In a conjugate beam, our beam, since it had fixed supports, it will be a free end. All right. So we'll end up with these diagrams. So this is PL. We have this one on the left side. Okay, let me use a different color. Okay, different color for that. So we have the left side. All right. Then you also have the right side. Again, a different. This ones will be going up, and then these ones will be coming. It's just green, but it's not working. And then this one also be coming now. AI. Then this also becomes. So we need to find our moments. MAB and an MB. Okay, so let's look at a typical scenario. So here, our interest will just be in trying to find summing forces. All right. So if you can use that summation of forces, let's say in the y direction goes to 0. So then we have PL over 4E. So this top triangle is just the base times the height, and the base is a length of L. The height is 4PL over 4EI divided by 2. Okay, and this is going upward. So minus the area of the two lower triangles. So it becomes MAB over EI again times L over MBA over EI again times L over 2. So now if you go back to the structure over here, if you look at the beam right here, this a symmetrical beam. The load is in the middle. The support conditions are the same. So it simply means that the end moment MAB and then the end moment MBA will be the same. All right. So we can assume that MB, so let's call each one of them M. All right. Minus, let's say M over, so let's say ML over 2 EI times 2. Okay, because there are two of them. And our M will become, if you find M, all right. So this here, are we safe? So this here is the same as MA. Below each fixed, oops, will give us the, what we call. If you have your Hibla book, I think I'll post it on the VCAM post if I have not already done that. But if you take your Hibla, I think the first few pages, let me see if I can share that for you guys to have a look. Just give me a second. Hopefully I can access that information. I think it should just be here. Okay, I have to search for it. I thought I had it close by. Okay, I've seen it. So let me just share that screen for us to see. So if you check the Hibla book, new share. Let me stop share first. Sometimes. Okay, so here we have. Come up. Okay. All right. So these are the fixed end moments. So we can see right here. Okay, I can't do editing on this one though. So we can see right here. Okay, let me highlight. All right. Oops. So the one with the yellow highlight is just what we did right now. All right. So the fixed end moment at AB is PL over 8, and then the fixed end moment at BA is PL over 8. All right. So the way the questions are is in such a way that you should just know what some of these fixed end moments are. All right. So when the point load is right in the middle, then the fixed end moment at both ends are the same. But if the load is skewed towards the right, in this case where we have length A and a length B, then this becomes your general equation for the fixed end moment. All right. And then this also becomes the general equation for the fixed end moments. Okay. So there are quite a number of them. 2-point loads, 3-point loads, a UDL along the entire span, UDL for half the span, and it goes on and then on. All right. So we'll take a break, some 10 minutes break, and then we'll come back and then continue from here. All right, so in the end, we now have moment values. So let's say if we take okay, so let me do it this way. Maybe that would help us. So we have MAB and then MBA. So theta A, delta, and then the fixed end moment. All right, so if we take, for example, theta A, our MAB was 4EI over L theta I, theta A over L. Now, if you take theta B, our MAB was 2EI over L theta A, and then B. Then for the delta, the one we just did today, MAB is minus 6EI over L squared delta. And then again, oops. This thing is annoying. Okay. So we have minus 6EI over Li over L squared. So I don't want to put any value over there. The fixed end moments, they change. All right. And then in all cases, just to take note of, this was clockwise, this was clockwise, this was good to take a note of. This was also, so the only one that did not have the same direction is this gentleman right here. All right, so they just pay attention to that. Hopefully I'm recording. Okay, great. All right, so now we need to sum everything up, which means that my MAB OEI minus 6EI over fixed end moment. Typically, this fixed end moment would end up being negative because of the fact that it is anti-clockwise. All right, but then we just put a plus sign regardless of that. Okay. So I can rewrite this equation here. Let's say if I want to maybe bring out 2EI, I can bring out 2EI over L. So that this becomes 2 theta A plus theta B for the MAB. Then, so let me put this one in. So this for the MAB. Then for the MBA, same approach. The MBA plus 4EI over L delta B minus square. Again, I can rewrite it MBA will be equal to, if I bring it to EI over L out, I'll do 3. minus 3 delta over L plus the fixed end moment. Calculations, we said that delta over L is the same as psi. All right, so some books will go further and rewrite these two equations as, again, or I can just write them here so that I don't need to do any extra work. Okay, so psi is equal to delta over L. So this equation then becomes 2ei over L 2 theta A plus theta B plus the fixed 2e plus 2 theta B minus 3 moment. All right, so these two equations, so let's say equation 1, this is equation 1, and this is equation 2. So the equation 1 and equation 2 are what you will need to solve for any particular beam that has two nodes. All right, the more the nodes, the more the number of equations that would end up with. Okay. All right, so let's all right. So far we've been dealing with A and B, or node A and node B. So what if we have a generic beam? So the same beam that we looked at, all right. But here, instead of node one, I can say, let's say node near. So this is a near node, and this is the far node. Assuming I'm moving from what's the name? A to B. So this is my near node, and this is my far node. So let me represent far with, I'm just replacing A and B with that information. So that simply means that the moment of near and far is equal to 2e far, and this fixed end moment is a near and far. So let me just go back quickly and then do a quick correction over here. So the fixed end moments, all right, so let me just do it that way for us. Okay, so this is AB, this needs to become different between, this can be, oops. So show us at what point these moments are. All right, option MF, sorry. So because of MFN L3 far and near. All right, okay. But most of the time, once you write this, the first equation, it takes care of the second one. All right. So for each span, apply twice. Span equations are applied twice, which means that if you have a beam with, let's say, member B twice, all right, so we solve for AB and solve for B, right? So that's something to take note of. All right, so once we have that done, so now we've been able to formulate the equations. Okay, the slope deflection equation. So the 2e is equal to 2ei over L into bracket 2 theta A plus theta B minus 3 delta over L plus the fixed end moment AB. That is one of the equations. All right, so in general terms, we could write the equation as this. Okay, and this becomes the slope deflection equation. Okay, so this is our slope equation. All right, there are different forms of this equation. We'll look at that later as we go along, but then we can always have different forms depending on how the structure is typically arranged. All right, so once we have this equation, how then do we use the equations to solve our problems? That is the end goal. That's what we need to do. All right, so to do that, we'll look at an example shortly. There are a few things to, let's see, if you have to solve a problem, I mean steps, right? A few things. So that's your first thing you need to do. Identify to do as the fixed end moments, and I don't need you to do that from first principle because books have that already done for us. Hebla, for example, the first page has that. I think I have that also on the V School. If not, I'll put it there before the end of today so that you can always go back and then have a look at it. Okay. So once you determine the fixed end moment, you also write later equations of data. All right. Then we'll formulate the slope deflection equations. Okay. So once you formulate the slope deflection equation, displacements all. Okay, it's back. Okay. So determine the unknown displacements and then also determine the internal end moments, right? So that's the MAB and then the rest. So reactions, and these diagrams, or they can be axial force diagrams. Are the steps to solving any problem using the slope deflection equations. All right. So the first thing is to determine what your fixed end moments are, and also write any equations of equilibrium. Then you write the slope deflection equations, and then you go on to determine reactions and then draw diagrams. Okay. So let's look at an example. Hopefully we have enough time to finish one example. So let's start an example. Okay. So this example, I'll try and fit in as much information as possible. Oops, that is a bad line. Take the screen sometimes to respond to. And that's the pain. Okay, so let me see if everything is working fine now. Okay. Okay. So let's say we have this right here. Explain to, oh boy, right here. What's the value f? Okay, so this is 22 kilonewtons per meter. Then I have a punch load right there in the middle, 135 kilonewtons. So these are my 6 meters, 3 meters, 3 meters. To show on the screens. So let me just wait for a bit. Okay, so they four come. All right, so 6 meters, 3 meters, 3 meters, and then okay. So now let's look at so let's say this is maybe A. This is A. And then we'll look at. All right, so the first step. So now we'll go through the various steps. Okay, so the first step, step 1, we are to identify all the node A. So let's take node A or node 1. All right, doesn't matter. So node A, all 0 equal to 0. Node C, theta C will not be equal to 0, but delta C is 0. Then if you take the node D, theta D and delta D conditions, how supports conditions are. So the only unknowns that we have for this particular situation here is to find theta C and find theta B. Okay, so we don't know what these ones are, so we need to find them. Are the only DOFs that we need to know, or we need to find because we don't know them. All right. Now the next item to look at, determine the fixed end moment. Okay. All right, so let's take span AB. If we take span AB, we have a UDL of span AB moments. All right. So what do we do? Oh, I close this. Okay, that's fine. I'll just open it up again. Hopefully the screen doesn't go off on me. So you share. Great. Okay. Let me try something else. New page. All the previous page that I opened. CENG. 25 minutes. Let's see. Okay. 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 So I think this should work. All right. So basically, if you look at the first scenario, what we have interest in is this guy right here. All right. This is pertains to span AB. So it means that the fixed end moment at the far right, the fixed end moments at the far right is WL squared. Let me just take away this guy. So the fixed end moment at the far right is WL squared over 12. So sorry, at the far left, and then at the far right is WL squared over 12. All right. So that's what we have. That's what we'll be working with. So we'll come back to structure here, and then the fixed end moments. If we looked at it, these are the directions they are in. So fixed end moment is over 12. All right. And then the fixed end moments UL squared over. Now let's take into consideration their directions. Okay. The MAB one is anti-clockwise. So that is negative. Okay. Whilst the one on the right hand side is clockwise, so that is positive. Okay. So let's just take note of that. So let me just change the 2 times 6 squared over 12. All right. And then that should give us minus 66 kilonewton meter. You can always cross check what's the name? Always cross check the answers. All right. Sometimes when I do them, I don't cross check. So just make sure that they're all correct. Okay. Then this becomes 22 times, this will give me 66 kilonewton meter. Okay. Now the next fixed end moment, the next one to look at is look at span BC. So with span BC, there's a point load of 135 kilo. It's 3 meters here, 3 meters there. So we want to know the fixed end. So this is A, this is B. So in our case, this is what? C and D. So the fixed end moment BC. So no, sorry, this is B and C, not C and D. Sorry. BC. So BC, we'll check the notes very soon. And then fixed end moment. The fixed end moment CB. This is minus PL over 8. And this is equal to PL over 8. Okay. So we can always cross-check with the table which has the fixed end moments. Okay. So I don't need to even go through this process. Just come down here. And then we'll find that example right there at the top. This is the example. Okay. So let me change the color. Okay, so you can see that right there. So on this side is it on the left hand side is PL over 8. On the right side is also PL over 8. Okay, now because the direction of your moment is negative, this becomes negative and this becomes positive. All right. Okay. So we go back to the fixed end moments, and then we place, so this then becomes minus 135 times an L of 6 divided by 8. And then we have, what's the answer? Let me see if I have the answer right here. So that'll give us minus 101.2 kilonewtons. And then this becomes 135 times 6 over 8, and we get 101.2, sorry, 25. So, now, if you go back to the other span, the span CD, right? So let's just add that one. So span CD, this is what we have. There are no loads on span CD, no external loads on span CD. Because there are no external loads on these spans, the fixed end moment CD and the fixed end moment DC will both be 0 because there are no loads, external loads acting on the structure. So that's something to take note of. Sorry, it's moment, so it always have to be in meters, kilonewton meter, right? So that is something to take note of. Now the next item, the number 3, is to look at the equations of equilibrium. Okay, equations of equilibrium. Okay. So you pay particular attention to the joints. So joint B and joint C, or internal joints, all right? Or I mean, just looking at joints in detail, all right? For joint B to be in equilibrium, then it simply means that all moments acting at those joints should be 0. All right. So one of the equations of equilibrium, let's say at B, means that all moments acting at B should be equal to 0, which means that MBA plus MBC should be equal to 0. All right. So I'm going to go back to the original diagram here and just show you. So here I have MAB. Here I have MBA. I'm messing things up. Forgive me. This is MBC. So these are all at the ends. This is MCB. This is and this is MCD, and this is also MDC. So when we take these joints, joint B, MBA and MBC should sum up to give us 0. That is what equilibrium stands for. And again, if you take MCB and MCD, when you sum them together at joint C, you should also get 0. Okay. So in this case, there are 2 equations of equilibrium. So here, summation of moment at C should be 0. So it means that MCB plus MCD is equal to 0. Please take note of the subscripts, all right? So it's always M near far, all right? So in this case, if it's MAB, then it means that we are looking at the moment at A with respect to span AB. MBA, we are looking at the moment at B with respect to span AB. Always take notes. The first subscript determines the point where we want to find the moment, all right, or the node. Okay, just so that we have that in mind. Okay. So once we have the equations of equilibrium written out, our next step is to now write the slope deflection equations. Slope deflection equations. All right. So we'll start with MAB. Okay. So MAB is equal to 2EI over L. So 2 theta A plus theta B minus 3 delta over L. So let me expand, plus the fixed end moments AB. Okay, so let's put in the values just so that we appreciate what is happening. Let me see if I can move this a little bit. Okay, great. So here, okay, now going back to the question, okay, so here EI is constant, so the EI for the various spans are the same throughout. Okay, in some cases that would not happen. The EI or the flexural rigidity will be different for each span. So please take note of that. Okay. And here the L is LAB. All right, so the span of AB. All right. So it becomes 2EI over A. The length of AB is 6 meters. Okay. From the first step, we mentioned that the slope at A is 0. So theta A is 0. Okay. So because of that, I can say that this becomes 0. Or let's say 2 times 0. Okay, because theta is 0. And that's the reason why we need to make sure that we identify all degrees of freedom or all unknown degrees of freedom, because that would inform us as to which one should be 0 or otherwise. All right. So plus theta B, which is not 0, minus 3. Our delta A here is 0. So over 6. Plus our fixed end moment at AB. The fixed end moment at AB is minus, let me just make this thing look good. It's minus 66. So this becomes minus 66. Okay. So this becomes one of your equations. Then we do MBA. So MBA flow the same idea. Again, 2EI over LAB, 2 theta B, take note of the subscript, plus theta A minus 3 delta over L, then plus the fixed end moments at BA. Okay, so this will give us 2EI. The EI is constant divided by 6 times 2 theta B plus 0 minus 3, 0 over 6, plus the fixed end moment at BA is 66 right here. Okay, so it becomes plus 66. Okay. Hold on for a second. All right, so let's continue. So we have MAB and MBE. All right. Now the next thing to look at is the MBC, and that'll be 2EI. So you just keep repeating stuff, right? But know where values end up with. So it becomes LBC. Then we have now 2 theta B plus theta C minus 3 delta over L. Again, this L is LBC, okay? Just so that if I didn't put it there, that's what it stands for. Then plus the fixed end moment at BC. Okay, so this again becomes 2EI. The length of span BC happens to also be 6 meters. This can change. But in this case, it's also 6 meters. So divided by 6. Then we have 2 theta B plus theta C, because theta C is not 0, okay? Then minus 3, 0 over 6, okay? The fixed end moment at BC was given as minus 101. So right here, minus 101.25. All right. So we come back here, minus 101.25. Okay. Then the EI 2 theta C plus B at CB. So pretty much just I'm just repeating stuff, but always take notes of the spans you are working with. So I get 2 theta C plus theta B minus 3 0 over 6. Again, take note of the minuses in front of the deflections, okay? And then plus 101.25. So we have 2 more to go. We have MCD over LCD. Now we have 2 theta C plus theta del C EI over delta C, but then the equation delta is also equal to 1 funny looking 4.5 plus 0. The fixed end moment at CD, we saw that to be 0. Okay, so that is 0 right there. Okay. Then you also write the last one, MD LCD delta of DC of 4.5, which is 0. Let me just put a 0 in there. And there goes the screen. Okay, so 2.5 plus 0. So these are your slope deflection equations. That is quite a lot. All right. So once we have these equations, then you can now use the equations of equilibrium to see how you can reduce. So let's say we have, let's say, equation 6 different equations. You only have 2 unknown degrees of freedom, right? Theta B and then theta C. So you need to what was it? You need to be able to simplify all of these to get an easy to work equation. All right. So this is where you apply the equations of equilibrium. So with the equations of equilibrium, it says that we should sum up MBA and MBC. So we should sum up MBA and MBC. Okay. Or if we sum these two up, we should get 0. In the same way also, if we sum up MCB and MCD, also you end up getting 0. So we can go ahead and do these summations. All right. It takes quite some time to get all of these done, but let's see what we can do. Okay. So if we sum up MBA and MBC, we will end up with so let me just expand it and sum everything up. So B equals 0. So it's going to be one long equation, but then the idea is the same. All right. Then plus 66. That's because all these are 0. So I mean, there's no need to bring them into the equation. Then for the MBC, so we are summing them up. MBC, we have 2 plus 2EI over 6 theta C minus 1 theta C. All of this should be equal to 0. Okay, so we can again simplify that approach. So if you have to simplify everything, you get what? If you sum these two, 4 over 6, so you get 8 over 6, right? So yeah, so we get 8 over 6 theta B. Bring my EI C. Okay, then we'll add the 1 6 and the 6 to the 101. I think we'll end up with when I get minus 35. So you get minus 35.25 equals 0. So this is a very simplified right. You could simplify it a bit more. 8 over 6 is the same as 4 over 3. 2 over 6 is the same as 1 over 3. I mean, those ones we can easily do them, okay? And then the next step is to sum, so MD equals 0, DC equals, no, sorry, I've made a mistake. Yeah, let me just correct it. MCD, MC 4 and 5. All right. The first case, I sum the equations or sum up equations. Okay. So let's continue. So if we do it that way, we'll end up with so MCB is what? So we have let's say over 6i over 6 theta b plus 101.I e theta c. This goes to 0. So we don't need to bring a. So then that'll be for the other side, right? 4ei, and all of this is equal to 0. Okay. So we can again simplify our equations, and then we'd end up with so we have 4ei over 6 theta c, and then 4ei. Am I correct? Yeah. So if you add 4 divided by 6 to 4 divided by 4.5, you get very funny numbers. So you end up with 14. So usually I prefer to write them in 5 equations. So here we can see that it's easier to just solve equation 7 and 8 simultaneously, right? And then find theta c and theta b. All right. So solve equations 7 and 8. Okay. So if we are to do that, what will we get? You can always use your calculator to do that. If we solve the two equations simultaneously, I think theta b will be equal to ei. You can see, we'll just cross check these values, all right? So these are your unknown slopes or unknown displacement. Okay. So if we go back to the steps, so we have now determined all unknown displacement. So we are still at step 4. Okay. So once we determine all the unknown displacements, we go back into our equations 1 to 6, substitute the displacement that we now know into these equations, and then find the moments. Okay. So for example, if I go to equation 1, so now let's look at equation 1, for example. Okay. So from equation 1, where is equation 1? Let me just copy that right here. Hopefully I can bring it. So let's say we come here. Everything seems to be slowing down. Wow, this is the longest wait I've experienced for this guy. Okay, finally. Hopefully it even works. So let's paste and then move here a little bit. Okay. So this is my equation 1, right? So I simplify it as over, all right, 6 I over 6. Have I made a mistake with something? Because then it should be, sorry, I think it should be over EI rather. I think it should be over EI. Let me make these corrections before I move on. So 45 points, I think 70. Okay. So then based on that, I'll end up with bracket E 6 minus 66. Do this minus meter. So this is meter. So this is for MAB. All right. So I can just go ahead and do something very similar for the other ones too. I don't know if I can copy without any issue happening. Let me see, is it gonna run? And there it goes. Okay. So the idea is about the same. You find your theta B and you find your theta C, or in general, you find your unknown displacements. And once you get your unknown displacements, you place them inside your slope deflection equations, and then you use that to determine the moments. Okay. So okay. So we'll have MBA E6 EI 66, and that should give me what do I have? Again, check my answers for me. I'm pretty sure I made them somewhere. So 96 points. Then our MCB will end up being the same as MBA, though. Yeah, it's easy to tell. Oops, I didn't copy everything. Okay, let me see. This was 6. There was brackets here. Okay, good. So it becomes 2EI, or I can just, okay, all right. So this will give me, if I put in the value of theta B and theta C as they are into these equations, I'll end up with minus 96.04, agrees with our equilibrium equations. Okay. So one of the ways to make sure that what you are doing is right is that if you sum the moment at a joint, if they sum, they need to be 0. So if you find the moment at the joint, there could be 1, and there could be 2, there could be 3, there could be 4 moment acting at a particular joint, or maybe a number of members meeting at one particular joint. When you sum all these moments at the joint or at a node, they should be 0. All right. So then we do for MCB. Sorry, this should have been MBC, not MCB. So this MBC, and then for the MCB, we'll do something very similar for MCB, and then we'll end up with 66 kilonewton. MCB and MCD should have the same answer, but negative. So this becomes minus 66. I think the theta C and theta B into the equations 1 to equations 1 to 6, 33 Newton meter. So we found all the equations, or all the values, all the moment, all the 6 moments. Sometimes some of them will be 0, some will be negative, or some will be positive. All right. So here I did not give you the value of EI, right? But in some cases, you could have the value of EI, maybe let's say, so let's assign maybe GPA, maybe 6 mm4. If that was the case, you can substitute these into the theta C equation and then find the actual angle, okay, measured in radians, okay. So you can put that to the equation and find theta B and theta C, all right. But because theta B and theta C are not necessarily the end goal, there's no need to find it, because otherwise their values are so small. They're usually in maybe like milli radians or micro radians or so, right? So it's best to leave your answers in terms of EI. It makes for easy substitution, all right. So from here, we can easily find our reactions. Okay, so finding our reactions is just like how we found the reactions when we were looking at the 3 moments equations. All right. So we now know our end moments. We can find reactions by looking at span by span. Okay. So let's say if we take span, so now I can change all of these because now I have used this, right? So span A. Okay. We assume that all our angles may be, or then easily find VA. got this span AB. So to do that, summation of, let's say, AB minus the 22 times 6 times 6 over 2 equals 0. So that's the summation of moment at B. All right. We know what MAB is, so it becomes 6VA minus MAB. MAB is minus 50.96, so it becomes minus minus. So minus 50 is going to us as 90.04. 22 times 6 divided by 2 will give us minus 396. And a VA of answers with a pinch of salt, but I think it should work. Yeah. Yeah, just I don't know. I should have had I should have gone through my calculations again, but I think my answer should be close, quite close. If not close, we can always go back and have a look at it. Okay, but at least the key thing is understanding the steps, and that's how we're going through all the steps. So in case there are any errors with my computation, just let me know, and then we'll look at it. So once VA is 72.5 kilonewtons, we can easily find the VB1, right? Maybe I'm looking at the wrong thing. Okay, so let me just write this answer here. Just so that okay, I think I made a mistake. Sorry, let's just go through it again. I think I made a mistake. Let me just correct it. The sorry, the MAB and then the MBA are in the same direction as our moment. Please forgive me. So this is actually plus, and this is plus. Okay. Somewhere in my head, I was thinking I was doing summation of moments about A rather. So they are both plus. So this is plus and this is plus. Let's correct that. This two remains as negative. So I'll end up with 396. 96.04. And then 50.96. Okay. Divided by 6. Just wanted to see what the okay, so sorry. So this is 58.5. Then means that VA plus VB1 will be equal to the 22 times 6. All right. So at this point, you are doing basic structural analysis. Okay, and nothing new. All right. So here our VB1 then will be equal to the 22 times 6 plus 50. We found VA, VB1. They also come to span BC, very similar to span BAB. So look at span BC. Where is it? That's a long. Okay. So again, we span BC. We have a beam B. All right. We want. So we also want to find VC1. All right. So again, very similar summation of moments at C equals. All right. So here becomes VB2 times 6 plus MBC plus MCB minus 135 times 3 equals 0. VB 6 VB2. So let's see what our MBC is. Our MBC is minus 96, so it becomes minus 96.04. Our MCB is 66, so plus into bracket 66.4, then minus 135 times 3 will give us 405 equals 0. So here our VB2 will be equal to, I think, the 72.5, and then VC1 will be equal to 62.5. Again, just cross-check these values. All right. Then the last span, which is span CD. So we have span CD. I'll be done shortly. I know it's 9. Time is up. So we have MDC and then MCD. There's no external load on it, so we just ignore that one. This is 4.5 meters. And we want to find VC2 and then VD. All right. So summation of moment at D equals 0. So we have VC2. All right, okay. So VC2 times 4.5 plus MCD plus MDC will be equal to 0 because there's no external load on the structure. All right, so there's no need to put any external load on it, please. So here our VC2, 4.5 VC2 plus our MCD. So we come back here, MCD is minus 66.4. Then our MDC is also minus 33. So into brackets, minus 33.2, and this should be equal to 0. Okay, so VC2 then will be 22 kilonewtons, and then VD will be minus 22 kilonewtons. Okay. So the total support, so for the support reactions, okay, so V1 or VA, sorry, VA then, oops, VA would be, that VA to be what, 58.5 kilonewtons. VB will be equal to VB1 plus VB2. So when you sum the two of them up, you should have, what's the name? I think we had 73.5 for VB1, and I had 72.5 for VB2. So that should give us 146 kilonewtons. Hopefully I'm correct. The VC is equal to VC1 plus VC2. Okay, so this will be 62.5 plus 22, and then we have 84 kilonewtons. All right, and then the last one, VD, is equal to minus 22 kilonewtons. So once we have all these reactions, we can easily draw the bending moment diagram and then the shear force diagram. Okay, with the shear force diagram, it's straightforward. Okay, so this is A, B, C, and D. All right. So our shear force diagram takes this form. And it goes up again, and it comes this way. So I'm going to put the values on top of it. So this is 58.3. Here's 73.5. This is 72. Oh, this should have gone up a little bit. Sorry. Okay, let me just, I'll correct it. And then here's 60. So here's 62.5. Then this is 22. Okay. So let me just move this one up a little bit, just so that it goes all the way to the top, at least a little beyond the 58. So something like that. So then this is so here's 72.5. Okay, so there's a shear force diagram. Okay. Again, let's just go through it. It's fairly straightforward to draw. And then we have the bending moment diagram. There are two schools of thought to draw the bending moment diagram. So because time is fast spent, I'll just sketch one. And then later on, we can, when we meet again next week, we can look at it a bit more into detail. All right. So the same idea. So this is A, B, then C, and D. Okay, let me start too close. So let's say B somewhere here. All right, great. So the bending moment diagram, it starts with a negative M value. Then it undergoes, so at the point where the shear is 0, you have your maximum bending. This has already been explained in basic structures. So maximum bending, then it bends this way. Oops, forgive my drawing. Just manage it like that. So We don't usually draw like that. We don't shade in drawings, okay? But just for simplicity's sake, all right? So we have something like that, and then this needs to go down a little bit longer. And then this one, I think this one went up too much. It's a bit funny sometimes drawing distance. So we don't shade, actually because of the pen I'm using. It's making drawing a bit challenging. So this is a straight line. It's a straight line, and then we have something like that. And it comes down to this, and then it goes to something like that. Okay, so this is how the bending diagram. Next week, that's the first thing we look at. We'll go through the diagram, but then just use this week to understand the values and all that. So 50.96, 96.08. So the color keeps changing. That's 96.08, and then I guess 25.48. This is we'll look at it into more detail. Then 66. Then this is 33.3. All right. So this is a bending moment diagram. All right. When we meet next week, we'll go through the example, like briefly to explain a few terms here and there. But then there's a general idea of how these calculations are done. All right. So we'll end here today. I will upload the video, make time, go through it in the course of the week. If you don't understand anything, just send me a message or whatever, and let's see how we can arrange for more clarification. But try and go through. But this is the very beginning of the entire course. So a good understanding of these calculations goes a long way to help us to appreciate the course better. All right, so I'll end here today. We'll meet again next week, Friday. Have a wonderful weekend.
Thank you, sir.
You're welcome.